Shooting it raw?
Yes. Shooting it raw.
So you want me to start that right now?
Sure.
Okay. So I'm an earth scientist. Earth science is a visual subject. In order to understand earth science, you need to see images of things, or preferably see the thing in person, but that's not always possible. I'm also a teacher, so I have students, and so from that perspective, photography for me is a means of creating information and passing that on to students and to readers and so on. So it's really useful from that perspective. Of course, I also find photography really important for personal reasons. I have a family. I like to see pictures of them and so on. In fact, I can report that I just had a grandson born just 2 weeks ago, and so it's really important to be able to see pictures of people. But mostly photography for me is to do with my work and teaching. And I'm not a great photographer. I've taken thousands of pictures with just a little point and shoot digital camera, and for the most part they're adequate. I don't really need super high quality images to do what I do.
Stephen Earle, thank you. That's it. That was great.
Okay.
Thank you for joining me on the podcast, a podcast where we talk about your images. It works in that we evoke, first of all, what the graphic is for people to imagine, and then they can look online to see the images. But more importantly, these are really great windows into your life and how you think. And hopefully that way we will inspire people, first of all, through your experience, and then to understand how you think and how you spend your time, how you make meaning of your own life. So welcome to Shooting It Raw. I really appreciate it.
Pleasure. Thanks
Great.
for inviting me.
Awesome. So let's just dive into your first photograph. And it's titled Annapurna, which is in Nepal. And the photograph is the super high impact images where it's like blue sky, incredible mountain with snow on the peaks. There's almost no vegetation, or there is no vegetation. So it's all gray, black, brown. And there's a trail, and on that trail there's somebody who's hiking. Full-on hiking gear, because the snow isn't abundant. I would say this isn't winter, although it's very high, so there is snow. And is that you in the photo? Off in the distance?
No, alas, this is not me. It's not my photograph. I was never there.
Oh,
but
okay.
But my son was there, and he took that photo, and I have used it for teaching purposes and other things. I wish I had been there.
Okay, teach me. What am I looking at? Why is this important?
Okay, so it's important. This is the Himalayas. It's the Annapurna region of the Himalayas. There's something over 100 peaks in the world that are higher than 7,000 meters, and all of them, every single one of them, is in the Himalayas. So it's just a most spectacular mountain range. But much more important than that, the Himalayas formed when India, we'll call it a subcontinent, a continent of India, converged with Asia, got pushed into Asia, and because they were two continents, neither one could go down underneath the other, so they kind of just pushed up this massive wall of rock that extends over thousands of kilometers. And as you can see from the picture, they're very rugged, beautiful. But from my perspective, and really from the climate change perspective, what's happening here is that these rocks are eroding, the rate of erosion, and you can see that in a picture where you can see where there's what we call talus slopes coming down the sides of the mountain, because pieces of rock are falling off of those steep slopes and falling and rolling down the mountain. So the rock of those mountains is being eroded into small pieces, and those small pieces are then being weathered, chemically weathered. And the really critical thing that's happening here is that as they're weathered, carbon dioxide is part of the process. It dissolves, becomes carbonic acid. It participates in the weathering process, and the carbon that was in the atmosphere gets taken out and goes into solution and is washed out to the sea. So when the Himalayas formed, and that started around 50 million years ago, it started an accelerated process of erosion and weathering here on the Earth. I mean, there were lots of mountains anyway, but as I said a little while ago, these mountains are head and shoulders.
Yeah.
Bigger, higher, more extensive than any other mountain range. And so the rate of erosion on Earth as a result of that collision between India and Asia, it became higher. The level of carbon dioxide in the atmosphere started to decrease as a result of that, and the Earth's climate cooled. So over the past 50 million years or so, there's been this progressive, not continuously progressive, but general decrease in the Earth's temperature.
Right.
That's why this image is important to me. It's just an example of that process, and it's important because that's given us the climate we have today. In the Eocene, the temperature here on Earth was 15 degrees warmer than it is now.
Okay.
And we know what 1 degree of warming is like. What it's done, it's scary. But to have something 16 degrees warmer, so a completely different world 50 million years ago in terms of climate. And not that it was a crisis, because it had happened slowly, had got warm slowly, and everything was used to that.
Right.
The crisis that we're facing right now is that it's happening quickly. And
right.
We're not used to it, and ecosystems are not used to it. So there you have it.
Just so that you can also have some background and context, you understand where this episode, where our conversation fits within the greater podcast library, I guess, is that I have personally 4 main interests. One of the interests is conservation and conservation science. I'm drawn to science. And so one of the, and right now the cluster of guests that I'm having is around climate science and climate change and just conservation more generally. And one of the previous guests also, he lives south of you. He lives in Oregon or Washington State. And his look was at, how are animals, how is fauna adapting to climate change? And, as you say, it's happening very quickly. And so some animals adapt, he gave some examples of Darwinian evolution, visible adaptation just because of hurricanes on this small kind of lizard. Right. So in your sense, in terms of your training, in terms of your exposure and worldview, you're looking at timescales that are extremely large, right? So when you look, like being in Canada also has, first of all, massive territory. So being on the West Coast, you're seeing much younger mountain ranges than, say, the Canadian Shield, which is much older. So in terms of this image here of the Annapurna, why does this kick off the conversation?
Well, generally I want to talk about climate change, but the work I've been doing is in understanding past climate change, and as you said a minute ago, understanding processes that happen very, very slowly and how they've impacted the Earth. So that's why this is important to me, because the processes that are exemplified by that photograph took tens of millions of years to actually make a big change on Earth. And obviously this kind of thing has happened in the distant past as well. But this is just kind of the most graphic, fairly recent example of it. I mean, we're going to look at a picture of the Rocky Mountains in Canada. And those mountains are like 150 million years old. They've been pushed up more recently than that. Yeah. So they're younger, in fact, than these Himalayas. Or older, I mean. And so, yeah.
So do you want to, so you want to move on to the next image, or do you want to say...
Whatever you want to do, sure.
Okay, great.
You're the boss.
Okay, from my Muay Thai training in Thailand and stuff, the general attitude is if we're not laughing, we're not doing it as well as we can be. So laughter is obviously very welcome. So let's move on to the next photo. So the photo number 2 that I have is Mount St. Helens, and this is a very dramatic photograph. It's in black and white. It seems like it's a scientific record in the sense that they're at the top of the right at the top of the frame. You could just see a sort of black arrow overlaid. This looks like a slide because it looks like a slide positive because the lettering's in white, and I don't know if I'm misreading this photograph, but it's in black and white. It's a photo of Mount St. Helens in the middle of insane eruption. So take it away.
Okay, sure. So yeah, it is a technical photo. It was taken by the U.S. Geological Survey from the air probably on May the 18th, 1980, which is when that eruption started. It started about 9 in the morning, and so I suspect they got up later in the afternoon and took this photo. I don't think it's that far into the eruption.
Wow.
So it's not a huge eruption. Interestingly, say it's about 1/10 as big as the 1991 Pinatubo eruption.
Oh, really?
In the Philippines. Yeah. So it's not really that big, but very close to home for us here on the west coast of North America. And also, it's in a populated region, reasonably populated, and so it had a dramatic effect on a lot of people. But what you see in the photo is this massive cloud of volcanic stuff coming out of the top of the volcano.
Yeah.
And what you actually see is tiny shards of volcanic rock. The morning this happened, I happened to be on my way from Saskatoon, Saskatchewan to Lethbridge, Alberta to visit my sister.
Oh, wow.
My wife and I were driving along, and gradually the sky kind of got dark and cloudy, and there was this yellow kind of cast to it, and there we could start to see dust coming down.
Wow.
And
how many kilometers away is that? A few hundred,
600 kilometers.
600.
We were traveling from one place to another.
Wow.
But we were like 1,500 kilometers away from Mount St. Helens, so a long way. Anyway, my brother-in-law worked in a lab that had an electron microscope, and he took some pictures of this glass or this dust, and it's really just tiny shards of glass. Anyway, that's not the point. That's what you see in this picture, but what you don't see, which is more important, is that coming out along with all that volcanic ash and glass are gases.
Yeah.
Water is the most abundant of the things coming out. Carbon dioxide probably second most, and sulfur dioxide third most. And those gases are all greenhouse gases. Well, water and CO2 are. Sulfur dioxide isn't. It does something different. But they affect the climate.
Right.
The thing with water, even though that it's the most abundant thing coming out of that volcano, is that there's a lot of water in the atmosphere. So the amount that's added during a volcanic eruption like this doesn't really make any difference to the climate.
Okay.
It's tiny compared to how much water there is.
Right.
Carbon dioxide, there's still a lot of carbon dioxide in the atmosphere, so even though that's quite abundant here, it doesn't make a huge difference.
Right.
We'll come back to that in a minute. The sulfur dioxide, on the other hand, the amount emitted by an eruption like this is probably more than there is already in the atmosphere.
Oh, wow.
Right around the world. So it makes a big difference.
A huge spike.
And that's why an eruption like this one not so much, because as I said, it's a small eruption. But say Pinatubo in 1991, they can really cool the climate, and Pinatubo did it. The Earth's climate average temperature dropped by 1.5 degrees for over a year.
Okay.
Following Mount Pinatubo. Wow. So a volcanic eruption has a cooling effect almost immediately.
Wow.
Then there's the carbon dioxide. Even though the amount of carbon dioxide being emitted by this isn't that big compared to the reservoir of carbon dioxide in the atmosphere, it stays there for a long time. So sure. Eruptions like this add to the CO2 in the atmosphere, and it builds up over hundreds, thousands of years. So if we had a period when there was higher than average volcanic activity that went on for thousands of years, that would warm the climate. Although each individual eruption would cool it a little bit, but generally speaking, over a long period of time, it would warm the climate. And that kind of thing has happened in the distant past, and has had some major effects on the Earth's climate.
Right.
Extinction-causing effects.
Wow.
At various times in the past.
Okay.
So this is just an example of that process. The important thing is to remember, on a short term, this cools the climate.
Right.
Although Mount St. Helens was too small to do much. And it only lasts for a few years. On a longer term, it can warm the climate as long as it carries on like that.
Right.
So
just because we've just met, this isn't an interview as much as it is a conversation, right? So
sure.
It's more like, okay, so the reason we met was I looked around and thought, well, who are the kinds of people I'd like to talk to? I reached out, you responded, and here we are. So thank you, huge thank you for that. As it happens, you live in BC. Now, what is your what led you to being you? Like, how did you become a professor or a teacher of climate? How did you land as that, as yourself?
I went to university. I started going to university in the early 1970s. I didn't know what I wanted to do. I went into science because I was interested in science and I was reasonably good at it. And then the first summer after my first year of university, a friend of mine managed to get me a job working in the mining industry in northern British Columbia, not mining, but actually doing mineral exploration.
Okay.
So I went out into the wilds of northern British Columbia. We flew in a float plane, flew all around the place in helicopters, got to hike through this amazing country, and I couldn't believe that they were actually paying me to do this.
Yeah.
And from that point on, I thought, wow, this is what I want to do. I want to be able to work in the field, and looking at rocks was, something I really enjoyed. And then later on, 30 years after that, I got into teaching, and I really love teaching. I think it's just an amazing thing to be able to do. I get an awful lot out of being able to transmit concepts and ideas and get people excited about the Earth and about so on. So that's kind of where I went, but that was earth science. I mean, I'm a geologist. I'm not a climate scientist.
Okay.
But then about 15 years ago, I started teaching a different course than the ones I had been, and it was called environmental geology, and I had to start reading a lot about it to kind of get ahead of it. And I realized then that we're in deep shit.
Mm-hmm.
And that we need to do something about it. And so that really changed my perspective on everything. And
wow.
I started wanting to move more into protecting the Earth than exploiting the Earth.
Sure.
And
okay.
So
I'm going to interrupt it for a second. one of the reasons why I stumbled upon your name was because of this dramatic, beautiful book cover. I wanted to burn into people's brains. What's the title of your book again?
Book is called A Brief History of the Earth's Climate.
Nice.
And there's a subtitle, Everyone's Guide to the Science of Climate Change. So it's about the natural processes of climate change that have taken place over billions, millions, tens of thousands of years. And so because we really need to understand those if we want to understand anthropogenic climate change,
sure,
what we're doing to the climate.
Yeah.
And also because, so many people that are skeptical about climate change, they keep saying, well, it's the sun, or it's volcanoes, or it's something else that's causing the climate change. It's not us. So, it's not our problem. We don't need to do anything about it. But if you understand the natural processes of climate change, it's pretty easy to see that, it's us.
Yeah.
For sure. And we have to do something to fix it.
Okay, so as we're talking, and you're opening these windows and doors, and for example, right now, as you're speaking, I'm looking at this dramatic, unbelievable image of Mount St. Helens erupting, and learning really about how you communicate and address the question of teaching and sharing a bit of climate science. So with me and with the listener, I'm looking at this really dramatic image, and to me, it's so telling of the kind of who you are, what kind of person inside you is like. Well, I've realized that this is really important and this is really valuable, and I want to connect those realizations to other people. And it's a service that you're doing, right? I talk a lot about service leadership. And so you're giving a service as a teacher to other students, but you're also giving a service as a human, as a citizen, or as a member of the community, to the people around you, to say, okay, guys, we need to, or guys, there's people where we need to do something about this. Like this is, so I find it so inspiring that that's how you spend your time. So, is this your first book, or is this many other books?
It's my first sort of trade book. I've written a couple of textbooks.
Okay.
Earth science textbooks, and and they're used in various places.
Right.
But it's the first time I've done something like this.
Okay.
And it was fun. I really enjoyed doing it. A lot of work, of course, but it was such interesting stuff to do that it wasn't work.
Right.
You talk about service. Really, it's selfish. I live here. I know we've got to look after this place for me.
Sure.
But I have children. And grandchildren, and I want them to be able to live here. But of course, it's for everybody too.
Yeah.
But it's I just want to say, not just service. It's selfishness to some degree, because I want to look after this place.
Well,
and we're not.
Just to share a little bit of how we talk about service, is that service isn't customer service or that. It's more of it's basically the connection that we give to one another within a network, as a human tribe or whatever. So, in a weird way, you said you have a grandson?
I do. Yeah.
How old is your grandson?
2 weeks.
2 weeks. Oh my, newborns. So this is something in my training where I talk about this. I say, well, believe it or not, as a grandparent or a parent, you give a parental or a grandparental service to this newborn so the newborn can survive. And oddly enough, that newborn is giving a newborn service right back to you, right? So that connection and energy explains how we connect with one another. And so by helping to raise or being included in your grandson's life, you're probably rediscovering the boot camp and the insanity of newborns and saying, okay, well,
not actually directly. this will be interesting to you. My son, who just had a son, lives in Quebec City.
Oh,
I
okay.
think you're from Montreal.
Yeah.
Yeah. So, and because of COVID and because of travel, I don't want to do much traveling.
Ah,
I haven't met my new grandson,
but you've seen him.
yeah. But I will. I will. I've
Yeah,
seen
yeah.
pictures. Yeah.
That's awesome.
Yeah. Yeah.
How about we take that as a strange segue to the next photograph?
Sure.
So the third image.
Oh, okay.
Okay, so it's called Robson Glacier.
Yeah.
Do you say glacier or glacier?
Glacier.
Yeah.
Glacier would be French.
Or British. I think British people say glaciers.
They
But-
might. Yes.
Yeah.
Yes. Possibly. Yeah.
Anyway, so Robson, I've never been to Mount Robson, but I'm assuming this is the one in BC.
That's right. This
Yeah.
is very near the BC-Alberta border in the Canadian Rockies. In
Yeah.
fact, the picture is not Mount Robson.
Oh, okay.
Mount Robson, the mountain you can see in the foreground on the right there is Rearguard Mountain.
Okay.
Mount Robson itself is just to the right of that,
Ah, okay.
but doesn't show in the picture. But the focus of the picture for me is the Robson Glacier,
Yeah.
which starts on Mount Robson and kind of wraps around the back of Rearguard Mountain, and you can see that in the middle,
Yeah.
in the middle distance there. Yeah, this is a really interesting image of change
Okay.
in the environment, and it's change that's taken place in this case over the last 20,000 years or so. So the last glaciation, the height of the last glaciation was about 25,000 years ago. At that time, the glacier, Robson Glacier, would have wrapped all the way around Rearguard Mountain and continued 20 kilometers down the valley and joined another bigger glacier down
wow.
there. So this whole valley would have been almost filled with ice.
Wow.
So then 20,000 years ago, because of changes in the Earth's orbital parameters, you might have heard Milankovitch cycles.
Well, assume you're speaking to a very dumb person. So what's a Milankovitch cycle?
Milankovitch cycles are periodic and very systematic timed changes in the tilt of the Earth, changed a tiny bit, but also the shape of the Earth's orbit around the Sun. It's an elliptical orbit, but it varies from being almost perfectly circular to just a little bit elliptical.
Right.
And those changes take place over tens, hundreds of thousands of years, and they have a significant effect on the Earth's climate. And it's
Sure.
those changes that made for the timing of the glaciations that we've had over the last million years. Glaciers have come and gone on a cycle of about 100,000 years.
Wow.
Anyway, so the last glaciation peaked at about 25,000 years ago. And then the orbit changed a little bit. I mean, it didn't. It's always changing in a very small amount. But the
Yeah.
change was towards more warming in northern latitudes. And so glaciers started to recede. And so starting 20,000 years ago, the Robson Glacier receded all the way back up and around and behind Rearguard Mountain.
Oh, really?
So
Okay.
if you were standing there 5,000 years ago at this spot, you would not even have seen a glacier.
Okay.
And then the cycle of warming switched to a cycle of cooling, and the glacier started to advance again. By the year 1300 or so, which is the beginning of what we call the Little Ice Age. You may have heard that term
Sure.
before. It's what caused there to be ice on the Thames and in all different parts of Europe. Anyway, that glacier that you can see there, it had advanced by 1300, and you can see down at the bottom left corner of Rearguard Mountain, there's kind of an arcuate shape of green trees across the valley, and the stream cuts through that. So that's where the glacier was starting 1300 years ago, and you can also see on the hill in the distance, there's this sharp boundary between eroded and non-vegetated stuff, and then above it more vegetated. So the glacier in AD 1300, filled that valley once again, but only as far as where that moraine is, that arcuate moraine
Right.
thing. And then it would have continued to expand down the valley probably, but starting around 1850,
Okay.
we started changing the climate.
Yeah.
So since then, between 1850 and now, this photo was taken in 2012, the glacier has receded again another 2 kilometers up the valley to where you can see it now.
Wow.
So there's been tremendous change
Yeah.
at this location over the last 20,000 years, and there will be more. And in the next 10, 20, 50, 100 years, it will again recede out of sight from this viewpoint.
Right.
But the important thing here is that we're looking at two different processes here. One is those Milankovitch cycles that I talked about that have had natural effect on the climate and have caused this glacier to recede and advance. And then starting 150 years ago, anthropogenic effects that
Sure.
have caused it and virtually every other glacier on the planet to recede dramatically.
Right.
And that's the problem that we're in right now.
One of the things that I absolutely adore is that here is this photo of a landscape image that by itself is dramatic. It's really beautiful. It's it shows huge country, like huge landscape, and then so that's one level. Then you, with your training and with your distinctions and your way of kind of you like how you read this image, because you have the extra language and concepts and whatever, reveals a story that is extremely rich and extremely historical in a sense, because as you pointed out, you can really see a line where the vegetation, like above the glacier, and that you can see that it's been carved away because of what you've learned and what you understand. You can actually project and rewind the sort of the film clip of the glacier growing and then receding again, which to me is just absolutely fantastic. I love it. Beyond, we must address anthropogenic climate change. Like, what other call to action does seeing this spark in your brain? When you see this, what is the main kind of? I'm sure there are many. Like, what are the many kind of impulses that spark in your mind?
Well, yeah, I mean, this is an indicator of climate change. This is just one of the many things that we can look at and say there's climate change. But it's more than that, because the glacier, you can see where it is in the distance there. Although it's a bit dirty in places, it's actually mostly white.
Right.
White surfaces reflect sunlight, and so when glaciers are large, a lot of the sun reaching the earth just reflects back into space and does almost nothing to heat the earth. But as a glacier recedes, a lot more dark surfaces are exposed, and that absorbs sunlight, that adds to the warming. So a glacier and glaciers in general are a beautiful feedback machine.
Right.
They accelerate warming in this case, but they also accelerate cooling. So as the glacier would expand, there'd be less or more bright surface, and so more light. So, and that's just one of a dozen important feedbacks that are part of the climate system. And people don't think about those too much. Really, they're the workhorses of climate change. It the changes that I talked about in the Earth's orbital patterns, they're very subtle. They just make a very tiny difference. But it's the feedbacks
Right.
that accelerate or drive the climate to change dramatically. And one of them is just the change in the area of glaciers. And as I said a while ago, this is just one glacier. There are tens of thousands of glaciers around the Earth, and they're all doing that.
Okay.
Virtually, one or two exceptions maybe, but 99% of them are receding, and as they recede, they're reflecting less light, so it's warming up. And the same applies, of course, to ice on the ocean surface. In the Arctic Ocean, northern Canada, Russia, Alaska, what have you, Greenland, in that area, the amount of ice covering the Arctic Ocean has declined dramatically over the last 15 years. And so when ice melts, dark ocean water is exposed, and there's a dramatic difference there, even more than in this picture here.
Sure.
Between the reflectivity of the surfaces. So that just makes warming accelerate even faster. But there are lots of other feedbacks that are scary.
How strong is that part of the science?
Oh, it's strong, but our understanding of it has evolved dramatically in the last several decades. I mean, people knew about feedbacks 100 years ago,
Okay.
maybe even 200 years ago, probably. But they didn't really understand the potential for that to change the climate.
Right.
And a lot of work is being done in this area now. So we do understand it better, and we do know that it's those feedbacks that have the potential to get out of our control. Now we know what we're doing to the climate. We're putting way too much carbon dioxide in the atmosphere,
Right.
way too much methane, and I hope that we can change that.
Okay.
And gradually decrease the way we're changing the atmosphere and bring climate change under control. But we don't know how the feedbacks are going to continue to work.
Right.
And there will, and possibly already has, and this will be a whole series of tipping points where what we thought was under control gets out of control because of feedbacks accelerating the climate change. And if we've crossed over one of those tipping points, and their tipping points are going to exist in a whole bunch of different ways, like in forest ecosystems, there's tipping points.
Sure.
And in all sorts of things. In the Arctic sea ice, tipping points.
Yeah.
If we cross those tipping points, it's going to become much more difficult for us to bring the climate back into a stable state.
Right.
So really important to understand these tipping points.
As a person who's trained at looking at geological time, which is, millions of years, and right now, can we say that climate itself ever does have a steady state?
So the first part of your question was, has it ever been stable? It has been stable for long periods of time, but it has always changed.
Yeah.
But the really important difference is the rate of change.
Right.
So it's changed dramatically in the past. I mean, there was a time 700 million years ago when the entire Earth was frozen over. The oceans were frozen over right down to the equator. There was hundreds of meters of ice on the surface of the ocean. Mm-hmm. And that lasted for 10 million years. So during that time, it would have been unchanging and just freakishly cold.
Yeah.
But eventually that changed and so on. But all of those changes are really slow. And, as you've heard many times, it's the rate of change that matters. And,
right.
And right now, the rate of change is just unprecedented.
Just to remind the listener, title of your book?
A Brief History of the Earth's Climate.
Yeah, we have to promote it. It's all about promotion. We have to get people burn that in their head. A Brief History of Climate. probably took you about a year to write or 2 years. Like how long did it take for you to write?
About a year to write it. Yeah.
Yeah. And how hungry were the publishers to grab onto it?
They jumped at it, actually. It's interesting. I live on a little island off the coast of Vancouver Island. The island is called Gabriola Island, and there's a publisher with their headquarters right here on this island.
Oh, wow.
New Society Publications, and they've done lots of this kind of stuff before. And they also do things on gardening but lots of climate books. And they were keen. So.
Right now I'm in Hong Kong, so in a place very far away, but I actually have a little plot of land on Savory.
Really?
I love BC.
Yeah.
Let's move on to the next photo.
Sure. Very different.
I'm eating this up. This is so good. Okay, so this one's called PETM Core. And it's like a slide which I assume you use in the classroom. There's a heading on top that says Ocean Drilling Program Core 1220B. I don't know what that is. There's a centimeter scale which starts at the absolute left at 40 and it goes absolute right to about 76 centimeters. And then you've got the earth, basically slices of earth that are on the left tan, then it's super, super dark, almost to black, and then kind of rusty, and then tan, like a clay sampling. And then at the bottom, it says 55.7 MA, and then within there it says Paleocene, Eocene, thermal maximum, and then it goes 55.8 MA. And please take it away. This is great.
Okay. So, Ocean Drilling Program, there's a multi-institution program of drilling cores in the seafloor. The title of this whole thing should be 3 Mountains and a Pile of Mud. And here's the pile of mud. The ocean floor is covered with sediments that have accumulated there over millions of years. And these are 55 million years old. It's quite deep into the ocean floor, but it's this absolutely priceless record of the Earth's history on the ocean floor. So this ocean drilling program was evolved to go out and sample the ocean floor and look at that stuff and do work on it. And so this is just one example. The core 1220B, the 1220 is the 1,220th drill hole that was drilled into the ocean floor, and since then there's probably been as many again by this one drilling ship. Anyway, so it's a section through the sediment that is accumulated on the floor of the ocean. This one actually comes from a couple of 100 kilometers southeast of Hawaii.
Okay.
That's not important. Because it's the same thing was recorded in similar core from many different places around the world.
Sure.
The Paleocene is one of the recent epochs, and it ended at 55.8 million years ago, and that's when we moved into the Eocene.
Right.
And this actually marks that boundary, and it's interesting because you've heard of periods and eons and eras and so on, and most of them are defined by changes in the fossil record. And this one is as well.
Yeah, I need to interrupt for a second just to say, like, listening to what you're saying and then just looking at the visual presentation of that earth core, or the sample, like, if the soil tells a story, it's what I'm looking at seems really dramatic, because the change between Eocene and Paleocene is like, it's not just like, oh, it kind of faded or whatever. There's a line. There's like, it's dramatic. So go ahead.
Yeah, so at the end of the Paleocene, there was a sudden warming. And we know that because samples taken out of this core and out of hundreds of other cores have been analyzed, and they've analyzed the proportions of oxygen isotopes
Right.
in those samples, and that is an indicator of temperature. And over the interval shown, the Earth's temperature went up about 5 degrees, 4 to 5 degrees.
Oh.
And
Oh.
yeah, so and that period of where the core is black is kind of the period during which it got really warm by that much. That's a huge difference.
Wow.
Um,
Yeah.
and it lasted, as you can see, for 100,000 years, 55.8 to 55.7 million years ago. And a lot of species went extinct, and there were a lot of changes, ecosystem changes in the oceans and on land all around the Earth at that time.
Yeah.
The reason that it's important and why I wanted to put this picture here is because what we're doing right now is not so different from what happened right at that boundary,
Wow.
55.8. There was a fairly abrupt, at least in geological terms, abrupt change in the Earth's temperature, an increase of about 4 to 5 degrees. When I say abrupt, it actually took place over 20,000 years.
Yeah. Yeah, but
And you compare that with what we've done. In 60 years, we've increased the temperature by 1 degree.
yeah.
In 20,000 years, naturally, at that boundary, the temperature increased by 4 degrees over 20,000 years. We've done
Yeah.
it a quarter of that in 60 years. That's scary. But
Yeah.
the really scary thing is that that triggered a series of changes, uh, feedbacks that caused this dramatic change in the climate, increased 4 to 5 degrees, and it lasted for 100,000 years.
Yeah.
And it's not very different from what we're doing now. In fact, what we're doing now is worse.
Yeah.
So go ahead.
I'm responding to you as somebody who's listening to what you're saying and connecting with it, and also the visual aid that you've offered, which is so powerful. So it's kind of like, okay, so you showed that that line is only about 20, is actually about 20,000 years of actual
Yeah.
time. And when you look at what, just visually what happens at that line, it goes dark. It goes almost black. Like
Yeah.
and then it's basically, it's like it's shades of brown. But yeah, so whatever happened in those 20,000 years and thereafter, it is something to be stressed about and panicked about because it is so dramatic.
Yeah.
So tell us why.
So yeah, so the sediments on the seafloor, it's mud, but it's made up of a bunch of different things. And the light colors in here are from shells of tiny creatures called forams or foraminifera that live in the surface ocean water or deeper water. And when they die, they sink to the bottom, and they're made of calcium carbonate, and they make the sediment light. When this change took place, it wasn't just a change in the temperature, the water warmed up, but also the amount of carbon dioxide in the whole Earth system increased dramatically.
Right.
And that increased the acidity of the ocean, which is happening now.
Yep.
And that changed the way calcium carbonate sediments behave and how soluble they are. So suddenly, whereas little tiny fragments of calcium carbonate were stable on the seafloor at this location, suddenly they became totally soluble. And so for the period when the sediment is black, there was nothing, no calcium carbonate was able to accumulate at this site. Gradually, the conditions improved, or at least changed,
Yeah.
and gradually, a little bit more calcium carbonate was able to survive here, and it gets lighter
Yeah.
towards the left, as you can see there. So it's a dramatic change in the composition of the sediment on the seafloor that reflects a change in the acidity of ocean water
Yeah.
during that period, but also massive temperature increase,
Okay.
die off of tons of things, and and a really important lesson to us that if we don't make some changes very quickly, then this kind of thing can happen and we won't be able to control it.
Yeah. These things are so complex, and
Yeah.
you've dedicated your adult cognitive life to wrapping your head around this. And I appreciate you even just sharing an hour's worth of that into something so the curious person can learn something. And so I appreciate it. When it's this complex, how are you able to work across different fields, looking at things like ecology and looking at other areas of science to broaden your understanding of, well, what is that impact really? I mean, because it's one brain can only fit so much. So how do you? It's amazing that humans can actually figure this out.
These things have been figured out by thousands, tens of thousands of scientists.
Sure.
So I'm trying to synthesize what these people have done over decades,
Right.
And make it something that people will understand, and so on. I have a fairly strong geological background, but biological or chemistry or physics, I'm weak. I try to understand as much as I can of those things as they are relevant to what we're looking at here.
Would you say the arc of this conversation follows kind of how you shaped your book? So let's transition to your book. What is the story that you kind of addressed in this book? And you're probably going to write another one, I assume.
Don't know. Not. Yeah, maybe.
Your publisher asked me to kind of push you, to nudge you. I'm joking, kidding.
So the book looks at not all, but many of the different natural processes of climate change, going way back, like changes in the sun and changes, plate tectonics and so on, and just summarizes all of those, talks about how those changes happened and why they're important and so on. And then the last couple chapters of the book talk about the implications for us, anthropogenic climate change, how it is similar to what's happened in the past, and how lessons that we have learned from studying natural climate change can be applied to studying anthropogenic climate change, but also how it's different.
Right.
And the difference, the main difference, the one that we should be most concerned about, is the rate at which it's changing.
Absolutely.
Because, as I said, it's unprecedented, and we really don't know what we're doing.
Right.
And we've got to stop doing it.
Yeah. Stephen.
Ran.
Good man. Represent. I appreciate it so much. Thank you so much.
Oh, pleasure. It was fun to do this.
You're great.
Okay. Well, thank you.
Shooting it raw?
Yes. Shooting it raw.